Let us begin very gently and very far back from the center of the topic, because when we explain transformers mathematically, it helps to remember what problem they were meant to solve. Before transformers became the dominant architecture for language, many sequence models were built around recurrence. A recurrent model processes a sequence one step at a time. It receives one token, or one word, then updates an internal state. Then it receives the next token and updates that state again. And so the model moves forward through the sequence, carrying a kind of running summary of what it has seen so far. This is already a beautiful mathematical idea. It says that rather than treating language as a fixed object all at once, we treat it as a stream. A sequence unfolds in time, or at least in order, and the model evolves with it. At each step, the model's state is meant to contain enough information about the past to help interpret the future. That sounds reasonable, and in many ways it is reasonable. Human reading also unfolds word by word. Human listening unfolds sound by sound. So recurrent models seem natural. But they carry a difficulty, and this difficulty becomes clearer the more carefully we think about long-range dependence. A sentence may begin with an idea whose meaning is only clarified much later. A pronoun may refer back to a noun many words earlier. A condition may be introduced at the beginning of a paragraph and resolved at the end. A poem may establish a pattern that only becomes visible after many lines. In mathematics, a definition introduced early may govern the meaning of an argument much later on. A recurrent model tries to preserve such long-range information in a state that is repeatedly updated. But repeated updating can blur information. It can compress too much. It can gradually forget. Even when clever variants were designed to reduce this difficulty, the basic structure still asked information to flow through many sequential steps. It is worth pausing here and reflecting on that phrase, many sequential steps. If one token at the beginning of a sequence needs to influence a token near the end, then under recurrence its influence travels through a chain of intermediate states. It is like whispering a message through many people standing in a line. Sometimes the message survives. Sometimes it becomes faint. Sometimes it is distorted. The mathematics of training such systems also becomes difficult, because signals used for learning must travel backward through long chains as well. So the limitation was not only one of memory in the everyday sense. It was structural. The architecture itself made certain forms of long-range interaction hard to preserve and hard to learn. And this is one of the great insights behind transformers. The breakthrough was not merely that models became larger. It was not merely that more data became available. It was not merely faster hardware. Those mattered, certainly. But the decisive mathematical shift was architectural. The transformer says, let us not force information to pass through a long sequential bottleneck if direct interaction is possible. Let tokens look at one another more directly. Let each part of the sequence decide which other parts matter for its interpretation. Let contextual dependence be built through selective interaction, rather than only through a running hidden state. That is a profound change. Instead of compressing the past into a single evolving summary and hoping the right details survive, the transformer allows many direct comparisons across the sequence. This does not remove all problems. Nothing in mathematics removes all problems. But it changes the geometry of the problem. It changes which relationships are easy to express. So when we speak of transformers mathematically, we are speaking about a class of functions and sequences that is organized around pairwise comparison, weighted combination, repeated transformation, and structured depth. And at the center of all of this is attention. Let us now turn slowly toward that idea. Attention is the heart of the transformer. It is the central mechanism, the defining operation, the thing that gives the architecture its distinct mathematical character. At an intuitive level, attention means selective relevance. When the model is interpreting one token, it does not treat every other token as equally important. Instead, it assigns different levels of importance to different parts of the sequence. Some earlier words matter a lot. Some matter a little. Some may not matter at all for the present decision. This is already familiar from human thought. When you hear a sentence, your understanding of a given word is not formed by averaging the entire past uniformly. You attend more strongly to what seems relevant. If the sentence contains a subject, a verb, a modifier, a contrast, a qualification, then different pieces exert different influences depending on context. The transformer turns this vague idea into a precise mathematical construction. Attention allows one token representation to interact with many others and to form a context-dependent mixture of information. That phrase is worth repeating because it is close to the essence. Attention forms a context-dependent mixture of information, not a fixed mixture, not a universal average, not a static lookup, a context-dependent mixture. The same word in one sentence may attend strongly to one set of neighbors, and in another sentence may attend to a very different set. So the operation is dynamic. It depends on the actual input sequence. This makes attention feel almost like a soft form of relational reasoning. Each token asks, which other tokens matter for me right now? And the answer is not binary. It is weighted. Several tokens may matter at once, each to a different degree. Let us say this another way. Attention is a mathematical rule for discovering dependencies inside a sequence. It builds a structured pattern of influence. It says that understanding is not merely about what objects are present, but about which objects should inform which others. And because the weights depend on learned comparisons, the architecture can discover structure rather than having every relevant dependency specified by hand. It can learn that certain words tend to depend on nearby modifiers, or on distant antecedents, or on delimiters, or on thematic signals spread across a paragraph. In this sense, attention is a mechanism for structure discovery. It is also closely tied to memory. Why memory? Because when a token attends to earlier tokens, it is in effect retrieving information from the sequence. It is not retrieving it from the model's stored parameters alone. It is retrieving it from the current input. The sequence itself becomes a temporary memory store, and attention is the retrieval rule. So attention is about relevance, about dependence, about memory, and about structure. This cluster of ideas is central enough that it is worth repeating slowly. Attention gives a token access to other tokens. It does so selectively, not uniformly. The selection is graded, not all or nothing. The grading is learned through comparison. The result is a weighted combination of information from the sequence. And this weighted combination depends on context. That is the heart of the matter. To make this more precise, transformers use three mathematical objects associated with each token. These are called queries, keys, and values. Let us spend time with them carefully. The language of query, key, and value can sound technical at first, but the underlying idea is quite simple once we sit with it long enough. Each token in a sequence begins as a representation, a vector of numbers. We are avoiding symbols tonight, but the idea of a vector remains important. It is a point in a high-dimensional space, or, if you prefer, a structured numerical description of the token and its current context. From that representation, the model produces three derived representations. One is the query. One is the key. One is the value. These are not three unrelated objects. They are learned transformations of the token representation. The model learns how to map a token into these different roles. Why three roles? Because attention can be understood as a matching and retrieval process. The query expresses what a token is looking for. The key expresses how a token can be found or matched. The value expresses what information the token offers if it is selected. That is a very good first intuition. Suppose one token is trying to determine what earlier part of the sentence it depends on. Its query describes the kind of information it currently needs. Every other token provides a key, describing the kind of content or role it represents. The model compares the query of one token with the keys of others. Stronger compatibility means greater relevance. Then the values of relevant tokens are blended together according to those relevance weights. So one may think of the query as a question, the key as an address or label, and the value as the content stored there. This is not perfect, but it is soothingly close. Mathematically, the comparison between query and key is usually based on an inner product. That is, the model measures how aligned two vectors are. Again, we are not writing formulas, but conceptually the operation asks whether two directions in representation space point in similar ways. Greater alignment suggests stronger compatibility. Lower alignment suggests less relevance. It is worth repeating that attention is built from learned comparisons. A token representation is transformed into a query. Other token representations are transformed into keys. Then compatibility scores are computed from these transformed vectors. These scores determine how much influence each token should have. And after that, the model forms a weighted average of values. So there are really two fundamental mathematical moves here. First, comparison. Second, aggregation. First, the model compares one token's query with all keys. Second, it aggregates the values using weights derived from those comparisons. This is elegant because it separates the questions of matching and content. A token may be highly relevant because its key matches well, but the actual information contributed comes through its value representation. This means the model can learn different spaces for deciding relevance and for transporting information. That flexibility is powerful. Let us slow that down even further. A token can be thought of as having multiple faces. One face says what it is looking for. That is the query face. Another face says what kind of thing it is. That is the key face. Another face says what it has to contribute. That is the value face. When one token attends to another, it uses the query of the first, the key of the second, and the value of the second. This may feel abstract, but it becomes intuitive with repetition. The whole structure says that language understanding can emerge from learned comparisons among token representation. Instead of giving the model a rigid grammar by hand, we give it a comparison and mixture mechanism and let it learn relational patterns. This is why people often say that structure emerges. The model is not told in a hard-coded way which words must depend on which others in every case. Rather, it learns geometric criteria in representation space. Similarity, alignment, compatibility, and useful association become numerical relations. From these relations, patterns of language can emerge. So when we say query, key, and value, we are naming three learned vector transformations whose combined role is to decide who matters, why they matter, and what information they contribute. The next question is obvious. Once we have raw compatibility scores, how do we turn them into usable weights? For that we need softmax. Softmax is one of the simple mathematical ideas that becomes enormously important because of where it sits in a system. After the model computes compatibility scores between one query and many keys, it has a collection of raw numbers. These numbers express comparative relevance, but not yet in a normalized or interpretable form. They may be large or small. Some may be negative, some positive. Their absolute scale may vary from case to case. What we want is a stable way to turn those raw affinities into attention weights. The weights should have several properties. They should all be non-negative so that the final mixture is easy to interpret as a weighted combination. They should sum to 1 so that the resulting average remains controlled in scale. And they should preserve relative preference so that higher raw scores lead to larger weights. Softmax does exactly this. Conceptually, softmax takes a list of scores and turns them into a smooth probability distribution. A larger score becomes a larger share of the total weight. But because the transformation is smooth, the result is not usually a hard winner-take-all choice. Instead, multiple tokens can receive partial attention. This matters deeply. If the model were forced to choose exactly one token every time, it would lose subtlety. Language often depends on several things at once. A word may depend partly on a subject and partly on a modifier. The interpretation of a phrase may require combining nearby syntax with distant thematic context. Softmax allows this gentle blending. At the same time, it still sharpens differences. A much higher compatibility score can dominate the distribution. So softmax balances two needs, selectivity and smoothness. It is worth repeating that normalization matters. Without normalization, raw comparison scores could produce unstable magnitudes. One token might end up receiving an extremely large total influence simply because the scores happened to be large in scale, not because the structural pattern warranted it. By turning the scores into weights that sum to 1, the model creates a controlled averaging process. This helps with interpretation, and it helps with stability. Let us pause and reflect on that word stability. In deep learning, stability is not a decorative extra. It is central. If one layer produces wildly varying scales, later layers become harder to train. If attention weights are not well controlled, information flow becomes erratic. Softmax imposes a kind of disciplined competition among candidate influences. There is also the idea of temperature, which can be understood conceptually even without formulas. Temperature controls the sharpness of selection. A low temperature makes the largest scores dominate more strongly, leading to more concentrated attention. A higher temperature spreads the weight more evenly, leading to softer attention. So temperature is like a dial for decisiveness. It controls whether the model makes a focused choice or a broader blend. Even when this parameter is not explicitly discussed in every transformer layer, the conceptual idea is useful. It reminds us that attention can be more or less peaked, more or less diffuse. And that matters for the type of structure being expressed. Sometimes a token needs to lock onto one specific antecedent. Sometimes it needs to gather a general thematic summary from many locations. Softmax makes both possible because it produces normalized weights while preserving graded distinction. Let us state the essential picture again. Raw affinities are computed from query key comparisons. Softmax turns those affinities into a normalized weighting pattern. The normalized weights tell us how strongly the token should draw from each available value. So softmax turns raw relational scores into usable attention weights. And those weights are interpretable. They tell us, at least in a rough sense, where the model is looking. Now that we have queries, keys, values, and normalized weights, we can describe self-attention itself. Self-attention means that attention is applied within a single sequence to itself. The tokens of the sequence attend to one another. Each token is both a potential seeker of information and a potential source of information. This is one of the most beautiful ideas in the transformer. A word is not interpreted in isolation. It is updated through its relation to other words in the same sequence. The sequence becomes a network of mutual influence. When we say self-attention, we do not mean selfish attention. We mean internal attention. The sequence consults itself. Each token starts with a representation. Then, using attention, it gathers information from other tokens that seem relevant. The result is a new representation for the token, one that now contains not only its original local identity but also some mixture of context from elsewhere in the sequence. This is why self-attention can be described as context construction. A token does not merely read context passively. It constructs its context actively by weighting other tokens according to learned relevance. This point is important enough to restate. Context in a transformer is not fixed in advance. Context is dynamically assembled. It depends on the token being updated. It depends on the other tokens present. And it depends on learned comparison rules. So if the same word appears in two different sentences, it may build two very different contexts. That is exactly what we want, because meaning depends on usage. Consider how soothingly general this mechanism is. It does not say that nouns must always look for adjectives in a rigid, hard-coded way. It does not say that pronouns must follow a manually specified search routine. Instead, it provides a general relational operation and lets training discover which interactions are useful. This is one reason transformers can capture both syntactic and semantic structure. Syntax concerns how parts of a sentence relate grammatically. Semantics concerns meaning and reference. Self-attention can support both because it is a general tool for context-sensitive interaction. A token can attend to nearby words for local grammatical structure. It can attend to distant words for long-range reference. It can attend broadly when it needs general topic information. It can attend narrowly when it needs a specific dependency. This flexibility is essential, and it is worth noting that every token is updated in parallel. Unlike recurrent models, which process the sequence step by step, self-attention allows all tokens to compute their attention patterns at the same layer simultaneously, provided the architecture's masking rules allow. This gives large practical advantages, but it also changes the mathematical perspective. The sequence is no longer a chain of updates. It becomes a field of interactions. One could almost say that a transformer layer is less like a traveler walking through a sentence and more like a conversation happening across the entire sentence all at once. Each token sends out a query. Each token offers a key and value. Weights are formed. Values are mixed. New token representations emerge. That is self-attention. And because this operation can be repeated across many layers, the context becomes progressively richer. Early layers may capture simple dependencies. Later layers may capture more abstract and global ones. The details vary, but the general idea is hierarchical refinement of contextual representation. Let us pause and reflect. Self-attention is the process by which each token updates itself using information from other tokens in the same sequence. The update is not fixed. It is input-dependent. It is based on learned comparisons. And it creates context rather than merely consuming a pre-existing context. This is a major conceptual advance. But one attention pattern may not be enough to capture all relevant kinds of structure. That is why transformers use multi-head attention. Multi-head attention sounds complicated when first heard, but its purpose is very natural. If one attention mechanism produces one pattern of relational weighting, then several attention mechanisms in parallel can produce several different patterns. Each one can focus on different aspects of structure. That is the idea of multiple heads. A head is one separate attention operation with its unlearned transformations. Because the transformations differ, different heads may learn different kinds of comparisons and different ways of transporting information. One head might become sensitive to local grammatical agreement. Another might capture long-range reference. Another might track punctuation or boundary markers. Another might gather broad thematic context. These are only examples, and we should not treat them as strict rules. But they illustrate the point. Multiple heads create representation diversity. Let us say that in a common way. A single mode of attention may not be rich enough. Language contains many overlapping relationships. So the model uses several attention channels in parallel. Each channel can learn its own relational viewpoint. This is not redundancy. It is structured diversity. That phrase matters. Multi-head attention is about richer structure, not mere repetition. If several heads were doing exactly the same thing, we would gain little. The usefulness comes from the possibility that different heads carve the sequence into different patterns of relevance. One can think of them as several mathematical lenses viewing the same data from different subspaces. The word subspace is conceptually helpful here. Since each head uses its own learned transformations, it is effectively working in a different arrived representation space. In one such space, certain alignments may matter. In another, different alignments may matter. So this same token can participate in multiple geometric relations at once. This is powerful because language itself is multi-relational. A word is not only a grammatical object. It is also a semantic object, a discourse object, a referential object, and sometimes a stylistic object. Different heads can, in principle, specialize in different aspects of this layered structure. Of course, the model is not handed these specializations explicitly. They emerge through learning. But the architecture makes room for them. It is worth repeating that multi-head attention should reassure rather than intimidate us. The basic attention mechanism does not disappear. It is simply replicated in parallel with different learned transformations. Then the outputs of these heads are brought together and combined. So the architecture says, let us compare tokens in several ways at once, gather several context constructions at once, and then merge them into a richer representation. This can also be seen as a remedy for the limitations of a single weighted average. One average can blur distinctions. Several coordinated averages can preserve more structure. Let us pause and reflect. Multi-head attention means multiple parallel attention mechanisms. Each head has its own learned query, key, and value transformations. Different heads can learn different structural patterns. The purpose is diversity of relational processing. The result is a richer representation of context. And because all this still rests on the simple ingredients of comparison and weighted combination, the architecture remains modular. Complexity is built from repeated simple ideas. But there is another issue we must face. Self-attention compares tokens, but tokens in a bare set have no inherent order. Language, however, is ordered. So how does the transformer know first from last, earlier from later, near from far? We need positional information. This is a subtle but essential point. Attention by itself is naturally permutation-friendly. If you only look at token content and allow unrestricted comparison, the mechanism does not automatically know where token occurs in the sequence. It knows what is there, but not in what order, unless order information is injected somehow. And language depends deeply on order. The sentence changes when the order changes. A definition followed by an example is not the same as an example followed by a definition. A negation before a verb is not the same as a negation elsewhere. Word order shapes syntax and meaning. So the transformer must encode position mathematically rather than assuming it implicitly. This is a very important idea. Order must be represented, not taken for granted. A recurrent model carries order in its very mode of operation because it processes tokens step by step. But the transformer, being more parallel and relational, needs an explicit way to make position available. This is done by adding positional information into token representations. Conceptually, each token representation is enriched with some indication of where the token sits in the sequence. Then attention can use both content and position when comparing tokens and constructing context. There are different ways to do this. One idea is absolute position. Each location in the sequence has an associated positional representation. So a token at the beginning receives one kind of positional signal, a token in the middle another, a token near the end another. Another idea is relative position. Instead of focusing on where a token is absolutely, the model emphasizes how far one token is from another or whether one comes before another. This can be especially natural for many linguistic patterns, since relationships often depend more on distance and direction than on absolute location. Let us sit with that difference. Absolute position tells a token where it is in the whole sequence. Relative position helps the model compare one token's location to another's. Both can be useful. Absolute information can help establish large-scale structure. Relative information can help express local and directional relationships. And both remind us that order is not free. It must be mathematically encoded. It is worth repeating because it is easy to overlook. Transformers do not simply know order. They are given mechanisms to represent order. Without positional encoding, the architecture would lose a crucial part of what makes language meaningful. This also reveals something general about mathematical modeling. Any property that matters but is not built into the base structure must be introduced deliberately. If your fundamental operation treats data as an unordered collection, but your phenomenon is ordered, then you must add order information somehow. The transformer is a clear example of this principle. So a token representation in practice is not merely a content vector. It is content infused with position. The model then learns how to use both. A nearby modifier may matter because of both what it is and where it sits. A long-range reference may matter because it lies in a specific earlier position. A repeated phrase may be distinguished by its place in the sequence. All of this depends on order becoming numerically accessible. Let us pause and reflect. Attention creates relationships among tokens. But tokens alone do not tell us order. Language requires order. Therefore, position must be encoded mathematically. And once it is encoded, attention can reason not just over content, but over content in sequence. Now, as we begin stacking many transformer layers, another challenge emerges. Deep models can become unstable. Information can degrade. Training can become difficult. This brings us to residual connections and layer normalization. When a model becomes deep, meaning it contains many successive layers of transformation, we gain expressive power but also face optimization difficulties. Each layer modifies the representation coming from the previous one. If these modifications are too strong, information may be distorted or lost. If scales vary too wildly, learning becomes unstable. Transformers rely on two architectural devices that help solve this: residual connections and layer normalization. Let us take them one at a time. A residual connection means that instead of replacing a representation entirely with the output of a layer, the model adds the new transformation back to the existing representation. So the old information is preserved and enriched rather than discarded outright. Conceptually, this is very gentle. A layer is not saying forget everything and become this new thing. It is saying keep what you are and now add a learned correction. That is a soothing idea and mathematically a very useful one. Residual connections allow information to persist across many layers. They make it easier for the model to learn small refinements rather than complete rewritings at every stage. This improves gradient flow during training and makes deep architectures much more manageable. It is worth repeating. Residual structure means preservation plus adjustment. Preservation plus adjustment. Not destruction and replacement, but continuity with modification. This is especially important when layers are stacked many times. If each layer can preserve a pathway for existing information while also contributing something new, then depth becomes more stable and more interpretable as progressive refinement. Now let us consider normalization. As information flows through many transformations, the scale of representations can drift. Some features may become too large, others too small. This can cause difficulties for optimization and for consistent behavior across layers. Layer normalization regulates this by recentering and rescaling representation components in a controlled way. Again, we are avoiding formulas, but the conceptual point is enough. Normalization helps keep the representation numerically well-behaved. One may think of it as maintaining balance. If different coordinates of the representation become too irregular in scale, learning becomes harder. Normalization keeps the system within a manageable regime. So residual connections preserve pathways, and normalization regulates scale. Together, they make very deep transformer stacks possible. This is not secondary engineering detail. It is part of the mathematical architecture. A powerful transformation mechanism is not enough. One also needs stabilizing structure that allows repeated application without collapse. This theme appears often in mathematics. A local operation may be elegant, but if we wish to iterate it many times, we need control. We need bounds, balance, continuity, stability. Residual connections and normalization play a role like that inside transformer design. Let us pause and reflect again. Attention gives powerful context-sensitive interaction. But repeated attention alone can be unstable in depth. Residual connections preserve information while allowing refinement. Normalization regulates scale and supports stable optimization. These devices make it possible to stack many layers and still learn effectively. And this leads naturally to the idea of the transformer block. A transformer is built from repeated blocks. Each block is a modular unit that combines self-attention with further learned nonlinear transformation, together with residual connections and normalization. This repeated block view is very important. It reminds us that a large transformer is not a mysterious monolith. It is a long composition of many copies of a relatively simple structural pattern. A block receives token representations. First, the attention part allows tokens to exchange information selectively. Then another transformation, often called a feed-forward or nonlinear mixing stage, acts on each token representation individually to reshape and enrich it. Residual structure preserves continuity. Normalization maintains stability. Then the next block begins. This repetition creates depth, and depth creates hierarchy. Why hierarchy? Because early layers can build simple contextual features, and later layers can build more abstract ones from those earlier constructions. A low layer may capture local syntactic relations. A higher layer may capture phrase-level or discourse-level patterns. An even higher layer may integrate broad semantic tendencies. This is not a rigid rule, but it expresses the general idea. Stacking blocks allows the model to construct representations of increasing abstraction. It is worth repeating that the power of the transformer comes not only from the attention mechanism in isolation, but from repeated attention and transformation. One layer gives one round of context construction. Many layers give successive rounds. The output of one layer becomes the input to the next, so relational structure can be refined, recombined, and lifted into more abstract forms. There is something deeply mathematical and almost meditative about this. A simple operation is repeated. Each repetition is stable because of residual and normalization structure. Each repetition slightly enriches the representation. Over many repetitions, complex behavior emerges. This is often how powerful systems work. Not through one impossible leap, but through many small consistent transformations. A transformer block is therefore best understood as a reusable mathematical unit for relational representation learning. Let us say that again in slower terms. A block takes in contextual token representations. It lets them interact through attention. It reshapes them through nonlinear transformation. It preserves continuity through residual pathways. It stabilizes scale through normalization. Then it passes the result onward. And the entire model is built from many such blocks. This modularity matters for theory as well. When researchers study what transformers can represent, or how information flows through them, or how depth changes expressivity, the block structure provides a clean unit of analysis. Now we are ready to ask a more theoretical question: what kinds of sequence transformations can transformers represent at all? This leads us into expressivity. When mathematicians speak of expressivity, they mean the range or richness of functions a model class can represent. It is a question about the family of input-output relationships available to the architecture. So for transformers, the question becomes, what kinds of transformations from sequences to sequences, or from sequences to predictions, can this architecture realize? This is a deep question. We will stay conceptual, but still serious. A model's expressivity depends on its architecture. It depends on the operations allowed, the way information can move, the kinds of nonlinearities present, the depth, the width, and the representation of order. Transformers are expressive because they combine several powerful ingredients. They can compare tokens flexibly through attention. They can aggregate information across long distances in a single layer. They can stack layers to build hierarchy. They can introduce nonlinearity through token-wise transformations. And they can represent order through positional mechanisms. Together, these create a rich family of sequence functions. It is worth emphasizing that architecture determines computable pattern families. This is not merely about parameter count. A model with many parameters but an awkward structure may struggle with some relationship. A model with a better structure may represent them more naturally. This was part of the earlier contrast with recurrent models. The transformers architecture makes long-range comparison more direct. That changes not just efficiency, but expressivity in practice. There is also a connection here to approximation theory. In broad terms, one asks whether a model class can approximate a target function arbitrarily well, given sufficient resource. For transformers, researchers study under what conditions they can approximate important classes of sequence mappings. These questions connect the architecture to classic mathematical ideas about function spaces, approximation, and representation power. But approximation alone is not the whole story. A model may be expressive enough to represent a pattern in principle, yet difficult to train to find it. So expressivity and learnability are related but distinct. Still, architecture affects both. Transformers also raise questions about generalization. A model may fit many patterns, but which ones does it learn efficiently from data? Which structural biases are built into the architecture? Attention encourages some forms of relational reasoning. Positional encoding shapes how order is handled. Multi-head structure promotes diversity of viewpoint. These design choices influence not only what the model can represent, but what it is likely to discover. So expressivity is about possibility, but also about architectural tendency. Let us pause and reflect. The transformer is expressive because it can build context-dependent interactions among tokens, combine them across depth, and encode order. Its architecture determines which sequence patterns are natural for it to compute. This links transformers to the broader mathematical themes of approximation, generalization, and representational limits. And yet there is another way to think about attention, one that often helps intuition. Attention is soft memory. The idea of memory appears throughout the study of sequence models, but in transformers it takes a particularly elegant form. A current prompt or sequence can be thought of as a temporary working memory. The tokens already present are available as possible sources of information. Attention is the mechanism by which the model retrieves from this temporary memory. This is why attention is often described as soft memory access. It is soft because retrieval is weighted, not exact. The model does not usually point to one memory cell in a hard, discrete way. It distributes attention across several locations according to relevance. So retrieval is graded and differentiable. It is memory because the earlier parts of the sequence remain available for consultation. This distinction helps clarify a common confusion. A language model has at least two very different kinds of memory-like behavior. First, there is stored knowledge in the parameters. During training, the model absorbs statistical structure from large amounts of text. That information is compressed into weights. This is long-term learned memory, if we use the word loosely. Second, there is prompt-dependent context memory. The current sequence inside the context window is immediately available through attention. This is temporary working memory. These are not the same thing. Parameter memory is stored in the model itself. Context memory is stored in the current input representations. Attention mainly governs the second kind. It is worth repeating because this distinction is extremely important for understanding large language models. When the model seems to recall something you wrote earlier in the same conversation, that is usually a matter of prompt memory, not parameter memory. It is using attention over the current context. When it seems to know a fact from its training data, that is a matter of stored parameters. So attention is a retrieval mechanism over a temporary context, while the parameters encode persistent learned structure. This makes the transformer feel less like a machine that simply processes a sentence once and more like a machine that continually rereads its own working notes. Every token can consult the available context to decide what matters now. And because the consultation is selective, attention behaves like a flexible memory retrieval rule rather than a fixed storage access pattern. A token may retrieve a very specific earlier phrase, or it may gather a broad average over several prior statements, or it may focus on recent local context. or it may bridge a long gap to recover something introduced much earlier. This is why the idea of soft memory is so helpful. It connects attention to something cognitively intuitive while remaining mathematically grounded in weighted averaging over sequence positions. Let us pause and reflect. The current context window acts like a temporary memory. Attention retrieves from that memory selectively. The retrieval is soft, meaning weighted and graded. This differs from the model's parameter-based long-term learned structure. Large language model behavior depends on both kinds of memory. Now we must discuss the size of that temporary memory. How much context can the model hold at once? And what does it cost to process longer sequences? A context window is the amount of sequence the model can directly process at one time. It determines how much temporary working memory is available for attention. Longer context is obviously attractive. With more context, the model can access more prior words, more previous turns in a conversation, more pages of a document, more steps of an argument. This helps with coherence, reference resolution, summarization, planning, and many other tasks. But longer context also becomes expensive. Why? Because standard attention compares tokens with other tokens across the sequence. If the sequence doubles in length, the number of pairwise interactions grows much faster than linearly. Each token potentially compares with many others. So total computational cost grows roughly like the square of sequence length. Let us understand that intuitively. If there are only a few tokens, each token has only a few others to compare with. If there are twice as many tokens, then each token has roughly twice as many potential partners, and there are twice as many tokens doing the comparing. So the total number of interactions increases very quickly. This quadratic growth becomes a major bottleneck for long context. It is worth repeating because it explains much of modern transformer research. Longer context means more available memory and potentially better behavior. But standard self-attention makes long context expensive because token-to-token interaction grows quadratically. So there is a mathematical trade-off between memory capacity and computational cost. This is not only a hardware issue. It is structural. The architecture's great strength, namely rich pairwise interaction, is also the source of its cost. One could say that attention buys flexibility by paying for many comparisons. That price is acceptable for moderate sequence lengths, but it becomes large for very long ones. This creates several practical design questions. How much context is necessary for a given task? How can one preserve useful long-range interaction without computing every pairwise comparison? What forms of approximation retain most of the benefit at low cost? These are mathematical questions as much as engineering ones. They concern sparsity, approximation error, locality, and structured reduction of computation. So when people speak of efficient transformer variants, they are not leaving mathematics behind. They are doing mathematics under practical constraint. Let us pause and reflect again. Context windows determine temporary accessible memory. Longer windows help because more prior information can be consulted. But standard attention becomes expensive on long sequences due to rapidly growing interaction counts. So the architecture presents a trade-off, richer memory access versus heavier computation. This naturally leads us to efficient attention methods. Because standard attention becomes costly for long sequences, many researchers have asked how to approximate or restructure it more efficiently. We will stay conceptual and calm here, because the main ideas are already quite rich. One recurring idea is sparsity. Sparsity means that not every possible token-to-token interaction needs to be computed. Perhaps each token only attends to a selected subset of others. If many interactions are unnecessary or negligible, then we can save computation by ignoring them. This is mathematically natural. In many systems, important interactions are structured rather than fully dense. A token may mainly need nearby context, plus a few special long-range links. If we can identify a sparse interaction pattern, we may reduce cost while preserving most useful information. Another recurring idea is locality. Language often has strong local structure. Nearby words frequently matter most. So one may design attention mechanisms that focus more strongly on local neighborhoods, supplementing them with limited longer-range pathways. This exploits the fact that not all dependencies are equally global. A third recurring idea is lower-rank structure. Very loosely speaking, this means that a large complicated interaction pattern may be approximated by a small number of underlying factors or directions. If the attention matrix, or the pattern of pairwise influences, has compressible structure, then one can approximate it more cheaply than by computing everything exactly. This is a beautiful mathematical thought. It says that apparent complexity may hide simpler latent organization. If so, the full dense interaction need not always be represented explicitly. There are also hybrid strategies. Some methods combine sparse selection with local windows. Some use compressed summaries of distant regions. Some divide sequences into chunks and pass information between them. The details vary widely, but the themes recur: sparsity, locality, compression, approximation. It is worth repeating that these are not merely implementation tricks. They are questions about structure. They ask what kinds of dependencies really matter, how interaction patterns can be compressed, and how much approximation error is tolerable. In other words, efficient attention is a mathematical design problem. How do we reduce cost without losing the essential function of attention? How do we preserve relevance-based retrieval while avoiding exhaustive pairwise comparison? How do we design structured approximations that match the statistics of real sequence data? These are deep and active questions, and they remind us that transformers are not a finished story. They are a living family of architectures, with ongoing work to understand their theoretical limits, their efficient variants, and their best formulations for different tasks. Let us pause and reflect. Standard attention is powerful but costly on long sequences. Approximation methods seek to retain usefulness while reducing computation. Common mathematical themes include sparsity, locality, and low-rank structure. So efficiency is part of the mathematics of transformers, not merely an engineering afterthought. Now that we have moved through these ideas one by one, let us return slowly to the whole picture and gather the threads together. A transformer is a sequence model built around attention. Attention allows tokens to interact selectively with one another. This selectivity is context-dependent. It is computed through learned comparisons between query and key representations. The resulting compatibility scores are converted into normalized weights through softmax. Those weights determine a weighted average of value representation. That weighted average becomes context. Self-attention means this happens within the same sequence. Each token updates itself by consulting other tokens. Multi-head attention means several such relational processes happen in parallel, allowing different structural viewpoints. Positional encoding provides order information, because sequence order must be represented explicitly. Residual connections preserve information while allowing refinement. Layer normalization regulates scale and supports stable deep learning. Transformer blocks repeat these ingredients many times. Depth builds hierarchy. Hierarchy builds abstraction. And the entire architecture can be viewed as a repeated mathematical unit for constructing increasingly rich contextual representations. It is worth repeating, because repetition is how understanding settles in. Transformers are not magic because they are large. They are powerful because their architecture reorganizes sequence processing around direct relational interaction. That is the structural shift. Earlier sequence models asked information to travel step by step through a compressed state. Transformers allow more direct dependence through attention. That is why they capture long-range relationships so effectively. They turn sequence modeling into comparison, weighting, and mixing across positions. And in doing so, they create a flexible form of soft memory. The prompt itself becomes a workspace. Earlier tokens remain available. Later tokens can retrieve from them selectively. This retrieval is dynamic. It depends on what the current token needs. And because context length is finite, there is a practical trade-off. Longer memory is helpful, but standard attention becomes expensive, which motivates approximate and efficient variants. So the mathematics of transformers touches geometry, approximation, normalization, hierarchy, memory, and computation all at once. Let us conclude very slowly now, and gather everything into one final conview. The transformer begins from a simple, but profound thought: the meaning of a token depends on its relation to other tokens. Not just the token itself, but its relations. Not just local identity, but contextual dependence. To make this precise, the model learns how each token should ask for information, how each token should advertise its relevance, and what information each token should contribute. These are the roles of query, key, and value. The model compares queries with keys. It turns those comparisons into normalized attention weights. It uses those weights to form weighted combinations of values. In this way, attention constructs context. Self-attention means the sequence is used to interpret itself. Multi-head attention means this interpretation happens through several learned relational viewpoints at once. Positional information ensures that order is represented. Residual connections ensure that information is preserved as layers deepen. Normalization ensures that scale remains stable. And repeated blocks allow the model to build layer upon layer of increasingly abstract representation. So the transformer can be seen as a machine for repeated contextual refinement. Each layer asks again, given everything available, what matters for each token now? And then again at the next layer. And then again. This is why transformers are so powerful for language. Language is full of dependencies, echoes, references, local structures, distant structures, patterns that only become visible when one part of a sequence can consult another. Attention provides exactly that mechanism of consultation. It is also worth repeating one final time that the decisive breakthrough was architectural. Scale matters, yes. Data matters, yes. Computation matters, yes. But the core mathematical change was the replacement of strictly sequential compression with rich context-dependent interaction. That is the central lesson. Transformers changed sequence modeling by changing the geometry of dependence. They made relation primary. They made soft retrieval central. They made context a constructed object. And from those ideas, an entire modern field unfolded. Let us rest there. Attention as selective relevance. Queries, keys, and values as learned relational roles. Softmax as normalized weighting. Self-attention as context instruction. Multiple heads as diversity of structure. Position as encoded order. Residual pathways as preservation. Normalization as stability. Blocks as repeated units. Depth as hierarchy. Context as temporary memory. And efficiency as the ongoing mathematical challenge of making long-range interaction affordable. That is the mathematical story of transformers told slowly. And if some of it feels abstract, that is all right. It is often in repeated listening, in hearing the same structure described from several angles, that the architecture begins to feel natural. So let us end with the simplest possible sentence. A transformer is a deep system that understands sequences by repeatedly letting each part of the sequence decide, in a learned and graded way, which other parts matter for it. And that gentle idea, repeated many times with stability and depth, is enough to build something remarkably powerful.